Recall that when we were graphing y equals functions of x, we were always able to plug in values of x and see how the inputs of x would affect the outputs of y. So on a function like y equals x minus 2 quantity squared minus 1, we had a couple of ways to graph this. We could graph this based off of the fact that the parent function is x squared, and then we could just apply the transformations that apply to this. Namely, the x minus 2 would cause me to move right 2, and the minus 1 would cause me to move down 1. Another way was at the beginning of learning to graph functions, we would plot values of x, or we would plug in values or inputs of x, and we would get the corresponding outputs of y and plot those. So let's take a look at our parent function first and recognize that x squared would have the point 0, 0, negative 1, 1, positive 1, 1. If I went further and plugged in 2, I would get an output of 4. And if I plugged in negative 2, I would get an output of 4 as well. So this would be our parent function that we can now shift to where it needs to be. So if we were to take every one of those individual points and move them right 2 and down 1, then each point would move right 2 and down 1. Right 2 and down 1. Right? So namely, the vertex in this particular case would move right 2 and down 1. But everything else follows, right 2, down 1. And finally, the point at 4 or 2, 4 would move right 2 and down 1 as well to give me this point. So we could see that this would be our function. Now this is great because we're able to see a graphical representation of what's actually happening with the inputs and outputs. But it has some drawbacks, because what if this particular graph or function described some path of a particle or a roller coaster or a ball being thrown, or whatever it might be? The problem with this is we don't know when it got to each of these points. All we know is that these are the points that we have. So this brings us to something referred to as parametric equations. Parametric equations are a set of two different equations that separately describe where the x coordinate is at a certain time and where the y coordinate is at a certain time. So more specifically, it's a set of points, or rather a set of x, y values, okay, where I find out that x can be found by looking at the function of t. And we could also see that y can be found by seeing it as a function of t. So instead of looking at a graph, namely y equals f of x, we're now going to be able to plug in t values to this function to find out the corresponding x's. And then we could plug in t's to this function to find the corresponding y. Now we're not saying that t is always time. Sometimes the t in trigonometry could be an angle. Sometimes the t could just be some other random parameter. Okay, so that's why we refer to t, where t is a parameter. So it's not really a variable, it's just basically saying that at given values of t, we're going to get given values of x and y, okay? Now when we look at the graph, okay, the graph of a parametric equation, the graph of a set of parametric equations, is referred to as a plane curve. And the reason we call it a plane curve is because, first of all, it's a curve that's going to be drawn in the Cartesian coordinate plane. Okay, and so we refer to that as a plane curve. Right. And so let's take another look at an example of how we can see a set of parametric equations and graph that parametric equation. So here is a set of parametric equations such that x is equal to t plus 2, which means if I plug in some t coordinate, let's just say that it's a time, I could find where the x coordinate will be at that given time. And likewise, if I take a look at the function of y, or the y as a function of t, I could also plug in a certain time and find out the y coordinate at that given time. So in order to do so, the best way to do this is to create a table. Now sometimes t will be allowed to be any value from negative infinity to infinity. But in this particular case, we see that we're only supposed to be plotting it when t is on the interval -2 to 2. So you could put any values in between -2 and 2, but we know that at -2 and 2, those are going to be the stopping points for this plane curve. When I plug in -1 and 0 and 1, those would be other good values to choose. So if we plug in -2 all the way to 2 into the function x, plugging in -2 gives me an x coordinate of 0. And plugging in -1 gives me an x coordinate of 1. Plugging in 0 gives me an x coordinate of 2. Plugging in 1 gives me an x coordinate of 3. And finally 2 gives me 4. So notice that x is in fact a function of t. Every input of t gives me an output of x. But we should also recognize that the values of t are also causing the x coordinates to increase in some particular pattern. If we now plug in those same values to t squared minus 1, then plugging in -2 and squaring gives 4, so 4 minus 1 gives 3. But notice that plugging in 2 will also give me 3. If I plug in -1, I get -1 squared, which is 1, 1 minus 1 giving me 0. But plugging in 1 also gives me 0. And finally, plugging in 0 for t gives me a y coordinate of -1. So now what we see here is just a list of ordered pairs. We see that it's going to start at the value 0, 3, and it's going to end at the value 4, 3. So 0, 3 is here, and 4, 3 is here. But one thing that's very important about plane curves as well is that you make sure to label the times. You label the parameter t equals -2, and in this case, t equals 2. The reason for that is that this is going to be better for us than a standard function of x, because it's not only going to give us a curve, but it's also going to tell us when the particle or car reached a certain location. All right, well, we also see that we have the point -1, or I'm sorry, we have the point 1, 0. And we also have the point 3, 0. Both of those occurred when I plugged in the point -1 and 1. And so I plugged the point 1, 0, which is right here, and 3, 0 is right here. So we're again going to label those. T equals -1 and t equals 1. And finally, the last point is the point 2, -1, which gives me the point here, which is at t equals 0. So when we would normally plot this as a full curve that goes on to infinity, something like this, and we would plot these points, go on into infinity, it turns out that that's not the plane curve. The plane curve doesn't go before -2 and it doesn't go after 2. So this is what we refer to as our plane curve. Notice that it begins at one location when t was equal to -2. and it ends at a location when t is equal to 2. But I'm sure that at this point you're recognizing that that looks like the same exact curve that we plotted in the original example. It looks like this curve is actually this function right here. So there's another thing that we're able to do once we create the plane curve by labeling each of our values and plotting the graph. We can also eliminate the parameter. So when we eliminate this parameter, what that's saying is, let's try to come up with the y as a function of x by eliminating the variable t, okay? Which in other words just means find y equals f of x. So the process of doing this is just like a system of equations where we're trying to come up with a way to substitute values of t into another equation. So this is where we write our functions here. First one we have is x equals t plus 2. Second one is y equals t squared minus 1. So notice if I could try to solve for t in one of these equations, then I could substitute that value into the other. Now it doesn't really matter whether we come up with y as a function of x or x as a function of y. We actually could come up with either. Okay, so I should probably state that as well by recognizing that I could say or x equals a function of y. The difference would be whether or not we solve for t in the x equation or solve for t in the y equation. Okay, so it looks like in this problem right here, the easiest thing to do would be to solve for t in the first equation, because all we have to do is subtract 2. So if I subtract 2, this gives me that the t coordinate is equal to x minus 2. Well, that implies that if t is equal to x minus 2, then I could replace the t in the other equation with x minus 2, which means that we're left with y equals x minus 2 quantity squared minus 1, which agrees with the function that we plotted over here on the right. But there's an issue here, because notice we should also be able to find what our domain is for our x, or for our x's and our y's. Since I know that t had to go from -2 to 2, then I can now look up here at my x coordinates and my y coordinates and recognize that I could state that x belongs to the interval, this is the symbol for belongs to, the interval 0 to 4. And we could also say that y belongs to the interval from -1 up to 3. So this is stating our domain and our range, right? So if I have this function, that would be defined for all values from -infinity to infinity. But because we were only looking at the values from -2 to 2 for t, then that caused us to now say that this is our domain right here. Okay, so we've eliminated the parameter to find what the actual function of x is, but we've also used a table to come up with all of the x and y points. So this now tells us something more than just the curve. But there's one last piece that we have to fill in here in order to make this our final plane curve. And this is to demonstrate on our curve the direction of travel. So we can see that this curve is obviously moving from -t equals -2 to t equals 2 by increasing that parameter. And so all we have to do is start putting arrows on here in order to show that it's traveling in this direction. Even though we've already placed our t values, these arrows demonstrate the direction of travel and are therefore important. One thing you do want to make sure of is, even if this happened to be -infinity to infinity, you want to make sure that even if this goes up like this, that you don't put your arrow tips pointing upwards. you still would leave those arrow tips off, and you would now show with these arrows that it's traveling in this direction. The parametric equations could also be in terms of theta. So the parameter t is just some random variable it's chosen, and most of the time it's t. But when we're dealing with trigonometric functions, we often say that the angle is theta. Since this is a trigonometric function in terms of sine and cosine, this is the reason why oftentimes we're given a domain for theta to be 0 to 2 pi. So that's why it would be a good choice to choose some values for theta, like 0 and 2 pi for sure, but maybe some points in between, like pi, or the quadrantal angles of pi over 2 and 3 pi over 2. And so notice that we're just plugging these in to our functions of x and y separately in order to find those corresponding points. So plugging in 0 for theta in this function here gives me an answer of 0. And so does pi, and so does 2 pi. So each of these theta values are going to give me x coordinates of 0. And now if we plug in pi over 2, notice that sine of pi over 2 is 1. So 1 times 3 gives me 3, while plugging in 3 pi over 2 gives me -1 times 3, or -3. So we can already see the domain for x is going to be from -3 to 3. So if we now choose some y coordinates for our function here, or find the y coordinates, at the same given theta values, notice that plugging in 0 gives me cosine of 0, or 1, times 5, which is 5. But that's going to give me the same exact value at the end when I plug in 2 pi. And if I plug in pi, cosine of pi is -1. So -1 times 5 is -5. So now notice that plugging in pi over 2 or 3 pi over 2 gives me cosine values of 0. So 0 times 5 gives me 2 values of 0. And therefore we can also see what the range is for this function, which would be -5 to 5. So now notice that we have a few points that we can plot. We can plot the point 0, 5 and 3, 0. 0, -5, -3, 0, and 0, 5. And so notice that 0, 5 starts here. It then goes to 3, 0. It then goes to the point 0, -5. And it then goes to the point -3, 0. Before it finally makes it back to this point right up top when I plug in 2 pi. So it might still be a little tough to tell what these values or what this function is going to look like. But what we can do is we can start to plot our t values. So we could say that this is when t is equal to 0, and this occurs at t equals pi over 2. This occurs at t equals pi. This occurs at t equals 3 pi over 2. And finally, I get back to where I started at t equals 2 pi. So it looks like it's going to be some closed continuous curve here. And secondly, don't be misled by the fact that this is the angle of pi over 2 instead of pointing upwards. And that this is the angle of pi instead of pointing backwards. Because these are just the points that we get when we plug in certain theta values. So since I still can't quite tell what the curve looks like, this is where I'm going to try to eliminate the parameter again. Now notice that because these are trigonometric functions, it's going to be a little trickier to actually solve for theta since we're going to have to take sine inverse or cosine inverse. But it turns out we don't need to do that. Let's notice that if we separately solve for sine and cosine in each of these functions, then we get that x over 3 is the same thing as sine of t. And we also see over here that y over 5 is the same thing as cosine of t. So instead of trying to solve for t in one of these equations and then plug it into the other, which would give me something like cosine of sine inverse, that would be pretty ugly. So instead, we think of an identity that relates the two. So notice that anytime you've got a function involving sine and cosine, we know that sine squared t plus cosine squared t is always equal to 1. So we can now plug in our sine t and plug in our cosine t and get our function. So sine of t is x over 3. Cosine of t is y over 5. So if I simplify this equation, this becomes x squared over 9, or 3 squared, plus y squared over 5 squared is equal to 1. And therefore we should recognize that this is an ellipse that spreads 3 units in the direction of x and 5 units in the direction of y, which now makes more sense as to why these were the points that we actually got. So if we were to graph this starting at t equals 0, we would curve down to get to t equals pi over 2, keep curving until I get to pi, keep curving until I get to t equals 3 pi over 2, and then keep curving until I get to t equals 2 pi. The last thing to do on our plane curve is to indicate the direction of travel by putting the arrows along our plane curve. And so notice that this set of parametric equations is much better for us than just getting the equation in terms of x and y, because this equation in terms of x and y only shows us the shape of the curve and therefore how the x and y coordinates relate to each other. But if this was describing perhaps the path of a NASCAR track, we could see that it's always moving in this direction, and we could see when it's going to get to certain locations based on our t values.